Okay, so the next piece we want to build onto this discussion is atmospheric circulation. And there are two really critical components that we need to build up that understanding. The first of those is that warmer air is less dense than colder air. That's true of most substances, that the warmer a substance gets, the less dense it gets. If you cool water down, it turns into ice. If you warm it up, it turns into vapor, right? And so that relates directly to this next key concept that warmer air can hold more water vapor than colder air, right? As we approach 100 degrees C at the right side of the graph here, 100% of water is going to go into the atmosphere effectively. Okay, and so warm air is less dense than colder air, and it tends to rise, creating this idea of convection. Convection occurs all throughout the Earth system, in the atmosphere, in the oceans, in lakes for that matter, and within the Earth's interior, as we talk about later. But with respect to the atmosphere, warmer air is less dense than colder air, and so it exerts less pressure, and warmer air also tends to rise. And so on the Earth's surface, if there's a zone of warm air next to a zone of cold air, the cold, higher pressure air will force its way into the lower pressure warm air, either causing the warmer air to move laterally out of the way or causing it to rise upward in the atmosphere. Okay, and so that's a pretty critical piece, and it leads to this idea of a single convection cell in either hemisphere, right? And that comes directly, if we look at this iPad drawing, from the fact that the Earth's surface is different temperatures, and it's emitting radiation, inversely proportional to that, and that's heating these CO2 molecules, right? There are little tiny CO2 molecules up here. There you go. There's some CO2 molecules that are absorbing and then re-emitting that radiation, right? That's happening all over the Earth's surface, or all throughout the atmosphere, rather. And so the temperature of the air across the Earth's surface is different. It's proportional to the wavelength of radiation that's being emitted by the Earth's surface, right? The lower temperature of the surface, the less heat energy is transferred to the atmosphere, specifically to the water vapor, CO2, and other greenhouse gases that have the ability to absorb and re-emit that radiation, right? That's what we've built up so far. So cold surface, because there's a low flux of energy, means there's cold air above it. That cold air is high pressure, right? And the warm air that overlies the tropics is lower pressure because it's less dense. Okay, and so if we just kind of view that as this idealized system here, really a non-rotating Earth, what we end up with is that air is going to move from cold, high pressure zones towards the equator in both directions, right? Now, that's not exactly what happens. Instead, we end up with a more complex circulation pattern, really resulting from the Coriolis effect and the fact that we do exist on a rotating sphere, not a stationary one. And so I'll end this video here, and I'll do another video that builds up that next kind of series of concepts. But it's critical at this point to understand that warmer air is less dense than colder air. Okay, and as a result, it exerts less pressure that can drive circulation in really two ways. It can cause lateral flow, colder air pushing in sideways into warmer air, like is shown by those black arrows there, or it can lead to warmer air rising, like in the case of a hot air balloon. Okay, and so if that, on this PowerPoint slide there, that surface current is shown, closest to the Earth's surface. But at the equator, in this intertropical convergence zone, warm air rises upward in the atmosphere. It cools off in the process, and then it moves laterally back to higher latitude. And that continuous circulation is maintained by the energy imbalance and the heat differential.